Thank you. I'm Yi Chen. I'm from the National University of Singapore. This work is done together with Ant, Pratik, Bin Chin, and Chun Wang from our departments. So there are two main keywords in this work, distributed computing and trusted computing. We want to securely carry out distributed computations, in particular MapReduce, using trusted computing. So in our setting, the cluster of servers live in a very hostile environment. The adversary can compromise the communications, can compromise the storage, and even the servers. Fortunately, for some servers, there is a small protected enclave where processes can be securely carried out. So now with all these protected enclave all around the place, we want to carry out the securely carry out the distributed computations. There are a few challenges. First, note that it's not safe to run the entire OS and application stack under the trusted environments. Since the code base is huge, it's very difficult for us to ensure that they are free for vulnerabilities. So we want to keep the set of trusted code to be small. So in our baseline system, we assume that the basic unit of MapReduce, that is the map and reduce functions, can be carried out in the hardware isolated process environments. Okay. And for example, recent work VC3 reported very recently in Oatlands is able to provide these environments. Other modules like the MapReduce, operating system, and hypervisor storage, we are all assumed that they are run under the untrusted environments. Okay. Data that are handled in the untrusted environment, they are all encrypted. They are only decrypted and processed under the trusted environments. So this leads to another question. Okay. So we have suppose we have the map and reduce that can be carried out in the trusted environments. So is this baseline system sufficiently secure? Is it just okay to just have a small little secure environment, and yet we can achieve the overall security for the distributed computations? Okay. So the answer is no. Okay. Why? Because there are interactions among the trusted instances can leak information. Okay. So even if the entire MapReduce ran in the trusted environments and the data are encrypted outside the trusted environments, the adversary can observe the interactions among the trusted instances. Okay. In the case of MapReduce, this will leak a lot of significant amount of information. Okay, before explaining that, I have to give a brief description of MapReduce. MapReduce is a programming paradigm. The programmer writes two programs, the map and reduce. There are three phases during the run times. During the map phase, each map instances take in an input and output sequence of tuples. Okay. And each tuple contains a key. During the shuffling phase, the tuples are rearranged with respect to their keys. All tuples of the same keys are grouped together. Okay. And lastly, during the reduce phase, each reduced instance will take in a groups and generate a tuples. Okay. So although this is sound very simple, it's very expressive, and is popular for big data computations. Hadoop is implementation of MapReduce written in Java. The first version contained 190,000 lines of codes, and the more latest version contained more than 1 million. Okay. So you may wonder why you need so many lines of codes. Okay. A large component of it is to handle the scheduling and tracking the computations so as to achieve efficiency and robustness. So now let's back to the security questions. Okay. We mentioned earlier that the interaction among the trusted instances leak information. To see that, let us look at well-known examples of MapReduce, that is word count. In these examples, the goal is to count the number of to count the occurrence of each word amongst all the files. Okay. During the map phase, each map read in the files and output a tuple for each word in the files. During the shuffling, the tuples are grouped with respect to the words. The words is the keys. Okay. And during the reduce phase, each reduce count and output the number of tuples it receives. And thus, we can get the occurrence of the words for among all the files. So over here, even if all the tuples are encrypted and all the map and reduce function is carried out in the trusted environment, the adversary still can observe the flow of the tuples. Although they can't figure out what is the content of the tuples, they can infer the relationship amongst the output of the map and the input of the reduce. And this will give a lot of information about the input files. For in the example of a word count, adversary can infer that, for example, the file F3 contains a unique word. Right? It can also infer that the F3 and F1 doesn't have intersections. In other application of MapReduce, for example, PageRank, where the input is a graph, by observing the interactions, adversary can infer the whole graph. So essentially leak the whole graph input files. Okay. So for data confidentiality, we want to hide these interactions, and that is our goal. So one possible solution is to use ORAMs, or previous RAMs. Okay. So in these solutions, the map will write the data, the tuple, to the ORAMs, and then read the tuple from ORAMs. Okay. So because ORAM is oblivious, so adversary is unable to correlate the read-write relationships and hence derive the relationship between the map and reduce. However, the overhead is very high. We give conceptually very simple solutions. In our solutions, we have a secure mixer. The mixer randomly permutes the tuple generated by the map, and next the tuples are grouped according to the keys under the untrusted environments. The keys are deterministically encrypted, so the grouping can be done based on the ciphertext. Next, the groups are sent to the reduce for reduce operations. For execution integrity, we need an additional step of verification to make sure that no tuples are duplicated or drops. Okay. Overall, these are the steps we have. First, during the map phase, each map instances read in the encrypted input files, okay, do the computations, and then output the tuples, the encrypted